Hello everybody, welcome back to Math 1351, more on math. Today we're going to discuss Chapter 11. We're going to start off with Section 1, which is basic notations. Then we're going to look at curves, polygons, and symmetry. And then we're going to end up with more about angles. Alright, Section 1, basic notation. The objectives here is we're going to understand the basic understandings of the undefined and defined terms in geometry. Basic geometry, geometric shapes, and notations associated with each shape, the attributes and properties of basic geometric shapes and the relationships among them. And we're going to end up talking about the names and classifications and measurements of angles. Alright, so let's begin. Actually, because we're dealing with geometry in this chapter, it's interesting to know that this topic of mathematics is the oldest of all mathematics being discussed. The two prominent names that you've probably heard is Pythagoras of Samos. That's an island in Greece. He lived about 500 BC. He pretty much discovered geometry. And then later on, the father of geometry, which gave him all the theories, the proofs, and everything, this guy named Euclid of Alexandria. Alexandria is a city in Egypt on the coastal side. It used to have the biggest library in that known history. Everything from science, military, histories, math, physics, everything that was discovered. Biology was, the copy of it was sent there and held there. It's kind of like the Library of Congress of its time. He lived around 300 BC. So this is how far along this topic's been around, and we're touching upon it so we can help our students learn it. Alright, let's begin. The fundamental building blocks of geometry are building blocks of geometry are points, lines, and planes. These are the basics, because a point, if you have a whole bunch of points, well, if you actually have 2 points, you connect them and you have a line. If you have a whole bunch of lines infinitely close to each other, you have a plane. So these are the defined terms. And we have everything else known as the undefined terms. And we'll get to those in a little bit. Right, so mathematics, again, it's a language, so we have to learn the terminology first. Let's talk about the terms and symbolism. For example, if we had point A, B, and C. Okay, notice, when we label points, they're capital letters. So we have A, B, C. They can be in a straight line, but they don't have to be. Let's see, I have a better picture here. So here's symbolism, and here's illustration. Points ABC are just dots. They really have nothing, no size, no shape. It's just a dot. A line is if you have two dots, 2 points, and you connect them. The lines go on infinitely, both ends. That's what the arrows mean there. You should notice the dots, the points are labeled capital letters. The lines are with lowercase, usually m, and it's italics. Planes. Okay, these are infinite number of points, infinite number of lines connected to each other. That creates a plane. And planes are always written in Greek letters. This is the alpha. It's the fish. Or, again, you can also name, since a plane has this characteristics, if you have three, these are called, okay, A and B are linear because they connect a line. A, B, C are nonlinear or non-collinear. Right, so this different ways you could represent points, lines, and planes. Those are the basic lines that we have. Points, lines, and planes. Let's look at a line. Okay, a line is determined by 2 points being 2 defined points. So when you're given these 2 points, there is one and only one. In mathematics, we use one and only one. One and only one. If and only if. To stress the point that it's very important. So when you have 2 points, there is one and only one line that connects them. Or we say contains them in mathematics. Because if you only have 1 point, there are an infinite number of lines that can go through there. I mean, any direction line. But once you have a second point, there's only one line that connects those 2 points. When we have 2 points, the line goes on forever, now both directions. We can talk about the distance. Okay, what is distance? It's a basic concept in geometry that allows us to measure the length, the magnitude between 2 separate points. So it's a basic concept in geometry. And it does this. This is how we would define a distance between these 2 points. If A and B are 2 points on a plane, It has to be somewhere, so we're saying it's on a plane. We can create a number line the number line AB such that there is a one-to-one relationship or we'll say mathematics we call it correspondence between the points. I'm sorry, I'm just getting over a very, very bad fever and maladies, flu type thing. Between the points on the graph, on the line, and the real number system. Remember, real number system contains of integers, whole numbers, decimals, fractions, everything like that. So, if A and B are 2 points on a plane, we can create a number line, A, B, such that there's a one-to-one relationship or correspondence between the points on the line. Because in order to have a distance, we have to have some numbers that correspond to it. Let's say then, if A begins at 0 and the point B is any non-negative. The reason we say non-negative, because you cannot have a negative distance. Distance is an absolute. Non-negative real number. Then the distance between points A and B is written as AB. So again, there's no line above it or anything. It's just AB. That's the distance between the 2 points. All right, let's have another table here for you. So let's look at these things. Remember, we have to know the terms and what they mean. So collinear points are points that are on the same line. They're collinear, on the line. So A, B, and C are collinear. D is not collinear to A, B, and C. So, remember I told you when you label a line, it's italics. So line L contains of points A, B, and C. Line L contains points A, B, and C. Points A, B, and C belong to line L. Points A, B, and C are collinear. Points A, B, and D are not collinear, or non-collinear. So basically, if you could draw a line between points, they're linear, or collinear, or linear, and if you can't, then they're non-collinear. A, B, and C are 3 distinct collinear points. Maybe they're all on the same line. Then B is between A and C if and only if A plus B, AB plus BC equals AC. Remember, when you don't have any lines, it means the distance. So the distance between A and B plus the distance between B and C is the same distance as distance from A to C. So from A to B plus A to C is the same distance as A to C. That's how you can tell that those points are all collinear, and then that B, since it's in both sets, B is between A and C. A line segment, or a closed segment. A line segment has two distinct endpoints. Is a subset of the line that contains 2 points of the line and all points in between those 2 points. So here's point A and point B. That's the line segment. It has a beginning and an end. When you write that, you have the beginning point, the end point, and just a bar above it. Remember, there is no direction, so I'm either going from A to B, that's what that one says, or from B to A, that's what that one says. Subsets of lines that are sometimes identified includes a half-open or half-closed segments, a segment without one endpoint, and an open segment. So here is the same thing we used in the inequalities. If you look at this line here, this line segment here, A has an open circle, so you can't use it, but we start at A and we end at B, and we can include B. So because we start at A and it's not used, so we put an open circle above it and a bar. The bar it tells us a line segment. And then since if both of them have closed dots at the end, then we have 2 dots at the very top of that. So it's symbolic. And if it's just a straight line, you put solid dots in both of them, then that means they're both included. Array. You notice above the A and B, it begins at A, goes past B, and it has one end is just a nothing, the other end is an arrow. So that means this begins at A and it goes past through B, goes infinitely that way. So array AB is a subset of line AB. AB has an arrow, the line above it has arrows both ends, so it goes on infinitely both directions. So it's a subset because the array AB is smaller and it's included inside the line AB. And it contains the endpoints A, point B, and all points between A and B, and all points C beyond it, such that A and C, 2 rays are opposite rays if they have the same endpoints, lie on the same line, and their union is a line. Okay. 2 rays are opposite if they have the same endpoints, lie on the same line, and their union is a line. So for example, the ray BA goes that way, and the ray BC goes that way. They go in opposite directions, and they share the same point. So that's how you can tell that it's going to equal a line. Half line is a ray without endpoints. Array without endpoints. That's interesting. Remember, array has one point that's fixed, and the other end goes on infinitely. Has one fixed point, and the other end goes on infinitely. A half line is an array without endpoint. A point separates a line into 3 parts: 2 half lines and a point itself. So let's see what that means. Half line AB denoted by BA with a dot over the B and the arrow over the A. Half line BC denoted by, it's B has an open circle but it's not included, and it goes on through C, and the point R. Not B, I'm sorry, RB. So reason what that means is, since B is included in both of those, It's a half line because since A and C are both on the line and B is the central connecting point, then B has to be between A and C. Since it's not included, they're equal half lengths. So it's going infinitely both ways. That's important to know, to remember that this line and this line, this ray and this ray are equal lengths because it starts at B and goes on infinitely. It starts at B and goes on infinitely. So they're half lines. Alright? The next thing we talk about are axioms. You're going to hear these words, axioms. These are statements that can't be proven. Okay, so here's some examples. 1. There is exactly one line that contains any two. There is exactly one line that contains any two distinct points. Here's point A and point B. And there's one line to prove it. I mean, you can see it's visually obvious, but and there's no proof for it. It's actually, that proof is not necessary. Look at another one. If 2 points lie in a plane, then the line that containing those 2 points is also in the plane. You have a plane, call it alpha. You have 2 points on that plane, A and B. Since you have 2 points and they're on a plane, then the line connecting those 2 points has to be on that plane. Again, it's common sense, but would have no proof for it. And the last one, let's see, we do 3. There is exactly one plane that contains any 3 distinct non-collinear points. Again, it sounds complicated, but when you look at it, it's very straightforward. You have a plane called alpha. You have 3 distinct points. You have A, B, and C. So it says A, B, and C. They're non-collinear because 2 of them could be in a line, but the third one can't. If C is on that line, then that's on that line, it's on the plane. But since these 3 points, A and B, are on the plane, and C is on the plane, and only one line connects A and B, then the 3 points are non-collinear. You're going to hear the word theorem. You're going to hear the word theorems used in math courses. What are theorems? Theorems are statements that can be proved. They can be proved by mathematical equations. 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 They can be proved by mathematical Theorems are statements that can be deduced using logic, undefined terms, defined terms, axioms, definitions, and previously proven theorems. Okay, we'll use the abbreviation there. So, theorems are statements that can be deduced. I mean, you can get to the answer by using logic, undefined terms, defined terms, axioms, definitions, and previously defined terms. Okay. What's a definition in mathematics? Definition is a term that's stated as simply as possible. A definition is something that's stated as simply as possible with properties that can be proven. Definitions are stated as simply as possible with properties that can be proven, omitted. In other words, the properties that of a term that you're using in a definition, it's omitted because it's understood. So, all right, let's look at an example here. Let's look at this. Lines through points. Given 15 points, no 3 of which are collinear. It's interesting. For me, only 2 of them connect the lines, the third one's not. How many lines are determined by pairs of those points? Okay, you have 15 points. How many different lines? How many lines are determined by those pair of points? So let's see what we have here. So let's do this by deduction. Remember, in order to prove a theorem, we have to do it by deduction, deductive reasoning and logic. So let's do the first one. We have 3 points. And we have 3 lines. Here we have 4 points. 1, 2, 3, 4, 5, 6. We have 6 lines. We have 5 points. And 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We have 10 lines. We have 6 points. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So let's see if there's a pattern here. So we have points, lines, 3 and 3, 4 and 6, 5 and 10, 6 and 15. Okay, this is interesting because if we look at each of these points, there are, in the first one, we have, how many arrows come out? We have 2 of them coming out of each one. This one, we have 3 going out of each one. 3, 3, 3, 3. This one, you have 4 coming out of each one. And this one, you have 5 coming out of each one. So, what's the connection? Because we're looking at a number of lines. 2 times 3 is 6 equals 3. Okay, so what do I do 6 to get 3? 3 times 4 is 12. What do we have to do to get 6? 4 times 5 is 20. What do we have to do to get 10? You see a pattern forming. 5 times 6 is 30. What do we have to do to get 15? So we have to divide by 2. And that makes sense because any line that we have has 2 endpoints. So instead of going from A to B and B to A, they're not 2 directions, it's only 1. So we have to take this product and divide by 2. There's only 1 direction. So we go, there are n points, and the number of actual connectors is n minus 1. If we have 3, you have 2. 4 is 3, 5 is 4. So n times n minus 1, and we divide by 2. This gives us the number of lines. So if n equals 15, then 15 minus 1 over 2, 15 times 14 over 2, 2 is no 14, 7, 7 times 5 is 35, 7. So if you had 15 dots, you'll have 105 lines. Ta-da! So that's how we use what we know already. All right. Let's keep on going. Okay. Next we'll talk about planar notation. A plane has no thickness. It's not like you can't say like a piece of paper because a piece of paper has a thickness. It's a plane it's just there. It's an imaginary concept. Extends indefinitely It is uniquely determined by 3 non-collinear points. So once we have 3 dots, those 2 are linear, those are not. So for those 3 points to be on the same plane, that satisfies number 3. It is uniquely determined by 3 non-collinear points. Now points, I mean. So, given, we have to use the word distinct again, given three distinct non-collinear points A, B, C there is one and only one plane contains the 3 points. This is pretty much a definition of how you define a plane. Okay, here we have these, just like this. Again, so terms and illustrations. Coplanar. Collinear are 2 points on a line. If they're coplanar, the points that are on the same plane. Non-coplanar cannot be placed on the same plane. So coplanar, co means together with. Coplanar lines are lines that have on the same plane. Skew lines are lines that cannot be contained in a single plane, and they're non-coplanar. So skewed lines are non-coplanar. Intersecting lines are lines that have exactly 1 point in common. Yeah, that's what we learned a long time ago. Concurrent lines are lines that intersect in a single point. So intersecting lines are concurrent lines. And here you see the graphics of it. Here we have a plane. We have points D, E, F, and G. We can see that D, E, and G are all on the same plane, so they're all coplanar. D, E, G, and F are non-coplanar because F is not on the plane. The line segment are the line DE, the line DF, and the line FE are non-coplanar. Let me see. DE, DF, FE. Okay, those are coplanar because they create their own plane. If you think about it, it's if I took here's the plane is the sheet of paper, and I have another plane right here. So therefore, they're coplanar on another plane that's not the original one. DE, DG, and EG are also coplanar because they're on this plane. And if we took another plane upwards, then the DF, FE, and DE are all coplanar on that plane. GF, GE, GF, DG are skewed lines because the point F is not on the plane. And so on and so forth. So again, it's once you understand these and see what they look like, if it's not on there, it's skewed. Two distinct coplanar lines are parallel if they have no points in common. A line is parallel to itself. Yeah, so that's interesting. A line is parallel to itself. Interesting. Two segments or rays are parallel if they land on parallel lines. Two segments or rays are parallel if they land parallel lines. So if we have two parallel lines, then we start anywhere with it and go one direction, have the ray there, then those two rays are parallel. Here's another one. We're going to look at relationships among planes and lines now. Alright, so if we have two distinct planes, it's like two sheets of paper. Or let's look at a walls in a room. Here's the wall, here's a floor. Where they intersect, two distinct intersecting planes have a single line in common. Where they intersect is a line. That's the crease in the wall, if it's up and down, or the floor is on the bottom. Two distinct planes are parallel if they do not intersect, same as lines. A plane is parallel to itself, same as a line. A line is either wholly contained in the plane, intersects it at one point, or has no point in common. That's all it could be. So we have, if you have a plane, a line can either, if it goes through it at any direction, it crosses at one place only. If it's on the plane, then it's all the points of that line are included. Or if it's not on there, this line here, HG, is parallel to plane alpha. So it's only three conditions possible. Either it's going to cross at one point, it's going to have infinitely many possibilities if it's on the plane, or if it's parallel to it, it has no solutions. Let's look at the symbolism they use here. Plane alpha is parallel to plane beta. That's plane alpha, this is plane beta. Plane alpha is parallel to plane alpha. Plane beta is parallel to plane beta. That's what I said. A plane is parallel to itself. Line FG intersecting with plane alpha is simply the point F. The line FG intersecting at point beta is only that point. Again, if a line intersects a plane, it's only that point. Line HG is contained in plane beta. Because it's on top of it, so it's contained in. It's a subset of. Line HG intersect with alpha. Here's HG. Plane alpha is up here. They have nothing in common, so it's an empty set. All right. A line and a plane are parallel if their intersection is an empty set. They don't have anything in common. So the line L is parallel to the plane alpha. The line M is parallel to the plane alpha. Because remember, if a line a line is parallel to a line to itself, and a plane is parallel to itself. So therefore, a line in a plane is parallel to that plane also. That's what this one says. A line contained in a plane separates a plane into two mutually distinct sets. Two half-planes and the line itself. A half-plane is a subset of a plane that contains all points in the plane on one side of the line. Let's look at those again. A line contained in a plane separates the plane into three mutually disjoint sets. Two half-planes and the line itself. Kind of if you take a piece of paper and fold it, you now have two halves of that fold and the fold itself. A half-plane is a subset of a plane. Yeah, so this half of the page is a subset of the entire page and contains all the points in the plane on one side of the line. So if I fold it, that half plane contains all the points on that side of the line. Yeah, it doesn't sound like much, but they were pretty happy with it when they invented it. Alright, let's talk about... Actually, we have one more, I believe. Let's look at this one. Next we're going to talk about angles, actually. So let's go and show this one. Because when you have two lines, that creates the distance between it, separating the two rays. An angle is a union of two distinct rays that share only an endpoint. Here's one ray here, BA, and here's a ray BC. They both have a common point, that's the vertex. The distance between those two sides of the two rays, that's called the angle. The rays of an angle are the sides of the angle, and the common endpoint is the vertex. So we have two rays. If they share the same endpoint, that endpoint is the vertex, and the rays themselves are the sides. The distance between there is called the angle. Now, notice, whenever we talk about the angle B, that's looking at the angle that's formed here. Or you could write it angle of ABC. ABC. The vertex is usually always in the middle. Makes it easier to read. Or CBA. Again, B is the angle in the middle. Or we can say, since we label this as 1, we say the angle of 1. They all mean the same. They're all equal. Angle of B, since B is the center point, what's that angle? It's the same as we labeled it 1. The interior of an angle whose sides do not lie on a single line. The interior of an angle whose sides do not lie in a straight line is a region in the plane encompassed by the two sides of an angle. Okay, let's take this again. Interior of an angle. So again, we know what an angle is. That's the distance between the two sides of the two rays that have a common point called the vertex. So the interior of an angle is whatever is in between the two sides, the two sides of the rays. The interior of ABC is a set of all points in the intersection of the half plane determined by BC and point A, and the half plane determined by AB and point C. So in other words, everything inside this Pac-Man's mouth, that's the interior of an angle. Adjacent angles. Basically, adjacent means next to. What it means here, if you see it, angle A, angle B, since this shares a common side, then they're adjacent. Adjacent angles are angles that share a common vertex and a common side, but whose intersections do not overlap, or interiors do not overlap. So we have two triangles here, with P being the common vertex. You have QPR, SPR. Since they both have a common vertex, then we have two separate angles, A and B. And since they share a same side, then they're adjacent. You can also say that the angle SPR plus the angle QPR equals the angle of QPS. So you say that the angle of SPR plus the angle of QPR equals the angle of QPS. So basically looking at the angle of alpha, the angle of beta equals, let's call it X. X is the overall angle. All right. Let me put those in the right order. All right. Angle measurement. As we said, an angle is measured by the amount of, what do we call it, opening between two sides that share a common vertex. Whenever you deal with angles, they're measured in degrees, x degrees. Right. For example, we know that a circle, we start in the middle, and we start moving. One complete revolution equals 360 degrees. We call it revolution because it revolves. It goes, starts and ends at the same place. So, 1 degree is 1/360th of a revolution. Now, how do we measure all this stuff? Because, yeah, we can draw the pictures and stuff. The materials we use, the mechanisms we use what's called a protractor. Protractor. You've seen these things before. They look like this. It's a semicircle with the middle opened up. You measure from the center. Yes, what you may see a protractor usually have a hole there. Measure from the center point. Center point on the straight side. To an angle that is desired. So you start your point here, it's in the center of the protractor, and if say you want to go to 50 degrees. So you put a dot here, okay, draw a line here first, you put a dot there, turn your protractor sideways, and draw that line. So now we know this angle here is 50 degrees. Now whenever we write, for example here, let's say this is A, B, C. We know this is angle of ABC, but the measure of angle ABC is 50 degrees. This just identifies the angle. Yeah. This symbol here we use a lot of times. That symbol is used. So sometimes you'll see me write either one of those. So let me show you. Here's an example of a protractor. You have a line. So the center of the protractor is here. I draw a line. I pick an angle here, say 30 degrees, put a dot there. I rotate my protractor and draw a line there. So then I know that the angle inside here, the measure of angle BAC is 30 degrees. Now, you have points between here. Degrees are broken down into, or subdivided into, minutes, which is 1/60th of a degree, and seconds, which is 160 times 60 is 36 hundredths of a degree, or 1/60th of a minute. So what this one says is, this is 29 degrees, 47 minutes, 13 seconds. You get, this way he gets it very, 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 very precise. And we're going to do an example of this in a second, of converting these things. So if you want to know the exact degree, instead of using all these, we have 29 degrees plus 47 over 60, because it's 1/60, plus 13 over 3600. Now these convert these into degrees, so your final answer will be in degrees. And you just calculate to figure that out. Right? So if we have a circle, there's a center point. Remember, one revolution equals 360 degrees. So let's say the angle between here is 50 degrees. That's from this point going this way to this way, so from A to B. This is my center. That's how I figure out the angles. But you can also go the other direction. Degrees are determined in a counterclockwise direction. We'll say angle degrees. But if we go the other direction, we call that a reflex angle. the degree of an angle in the clockwise direction. And the way to figure that out is 360 degrees minus the angle. So 360 degrees minus 50 degrees equals 310 degrees. That is the reflex angle. Let's look at an example here. In the figure below, find the measure of BAC. That's how tall the flag is above the building. If the measure of angle 1 is, so this big one is 47 degrees 45 minutes. And the measure of angle 2 is 29 minutes, or 29 degrees 58 minutes. And then express this as number of degrees, which we just did. Okay, so we want to know what that is. The way to figure that out, so for the first question, we take 47 degrees 45 minutes minus 29 degrees 58 minutes. You can't take 58 minutes for 45. So I have to borrow a degree. Remember, 1 degree is 60 minutes. So if I took 1 degree from there, and I have 46. I add 60 to 45, so 45 plus 60 is 105. The same when you're subtracting. If you have to borrow one from the tens to the ones, or the hundreds to the tens. So 105 minus 58. 15 minus 8 is 7. 9 minus 5 is 4. So it's 47 minutes. 16 minus 9 is 7. 3 minus 2. So the measurement here is 17 degrees 47 minutes. And the second one, this says convert 47 degrees 45 minutes 36 seconds into degrees. (47) 45 over 60, because that's minutes. 36 over 3600. Let's see. Let's simplify these. 5 goes into 45 9 times. 5 goes in here 12 times. 3 goes in 9, 3. 3 goes in there, 4. So 3 over 4, 36, 36. So this is 1 over 100. This is 47 plus 3/4 is 0.75. 1/100 is 0.01. So it's 47.76 degrees. And that's how that works. Alright, let's see. Let's talk about angle creation. No, it's not that one yet. So let's look at a sheet of paper. Fold it once. Open it. So if the sheet of paper is a circle, let's say it completes the 360 degrees. If you fold it in half, that half part is the half of 360, what equals the 180 mark. So again, a 180 mark it's called a straight angle. Because we always talk about circles. So if you fold this in half, here's the center. Always start from here. If we cut in here, all the way around is 360. So halfway around is 180. That's why they call it a straight angle. If you fold it again, vertically now, if you fold it again, so we folded it again. So half of 180 is 90. So at this point, that's nothing. You start from 0. Go up here, that's 90 degrees. So we know each quarter is 90 degrees. So 90 plus 90. 180 plus 90 is 270. That's down here. 270 plus 90 is 360. So that's how we figure it out. So this is a right angle. Acute angle. Acute angle is any angle less than 90 degrees. Now you see why, is this an angle or is a less than? From now on, whenever we talk about angles, we'll use this. So this is any angle less than 90 degrees is an acute angle. Actually, it's any angle between 0 and 90. An obtuse angle any angle between 90 degrees and 180 degrees. So this is the important part for a straight line. Because if you think about it, in a straight angle, if you, this one's acute, let's say it's 70 degrees. This one's obtuse. Since this is 180 degrees, and that's 70 degrees, so it's 180 minus 70 equals 110. So this one's going to be 110 degrees. It's bigger than 90, so it's obtuse. Now, any two angles if you have any two angles add together to equal 90 degrees, are called complementary angles. So if two angles equals 90 degrees, then they're complementary. If you add them together to equal 180 degrees, then they're supplementary. Those are supplementary angles. Yeah, let's see how many more pages we have left. Okay, easiest way to remember this. Now P equals 90. Complementary has one P, so it equals 90. Supplementary has two P's, so 90, 90 equals 180. Let's see here. I have the sheet. An acute angle measures less than 90. A right angle is exactly 90. Obtuse is greater than 90 but less than 180. And a straight angle is 180 degrees. Alright, so that's very important for us to figure that, remember that, is because we have to, again, it's words. If I say, okay, find me two acute angles, or give me, is this angle obtuse or not? So we have to know the definitions of them. angle formed by rotating a ray. Now, let me tell you a story also. We have our center here. We always start to the right. It all has to do with where it all started. Remember I told you Pythagoras and Euclid? Well, those guys were 5, 6, 7, 800 years ago. Now, all they had to deal with time were sundials. And for them, the day started in the east. That's when the sun rises. That's why they have to start here. What does the sun do? It goes up. The sun goes up. Top of the day it's there, and then it sets to this way, and then it goes around to the other side. So that's the reason why when we deal with angles, we always go this way. So this way are positive angles. So if you're going this way, those are negative angles. What if you had a measure of an angle, let's say A. What if can you have one that's greater than 360? So if the measured angle is greater than 360, then you have let's say more than one revolution. So let's say your angle A was, the measure of angle A was 415 degrees. We know that one complete revolution is 360, so 415 minus 360 . So once you go all the way through, what you have left so this one's the same as 55 degrees. Because one complete revolution doesn't do anything for us. It ends back at there, at 55 degrees. Circles and arcs. As we defined circles in algebra, a circle is an infinite number of points that are all equidistant from a center point. This equidistant is the radius. The center point is the center. So what's an arc? Any point on a circle that can be drawn without lifting your pen. So here we have the center point. There's the radius. So no matter where you go, as long as you start from here, the radius is still going to be the same. It's going to be a point on the line. Now let's look at these words here. So we know from the center to the circle, we call that the radius. A line that goes through the center across to the other side, that's called the diameter. The diameter, as we can see, is twice the radius. Radius r. So the formula for diameter is twice the radius. So we'll call that the origin A, B, C. That's some angle. A line that cuts through a circle, not going through the origin, is called a chord. It's also called a secant. A line on the outside that just touches the graph, the circle, at one point, that one's called a tangent. The arc, you have 2 points. That is the arc. So it's created by, you have a line, a radius, from the origin to some point A, and it goes up some angle to stops another point. That distance, that point traveled, is called the arc. So the radius is from O to A. It's a line segment. The diameter from C, from B to C to C to B, let's go B to C, it's a line segment. The arc is going from A to B. It's got an arced shape symbol. So when you see the little arc shape symbol, that means it's the arc of those 2 points. Alright, so let's see. I'm just have another worksheet here. No, that's coming up. Yeah, here's, okay. Okay, now this one says here, find the following measures. The measure of arc AB associated with the central angle AOB. AOB. So we have to figure out, in order to know this arc length, we have to know that length, that arc, the degree. How do we figure that out? Well, since we know we have a line here, FB. Here's F, here's B, and there's A. So, since this is 60 degrees, and the straight line is 180, so this has to be 120. Because 60 plus 120 has to be 180. So the measure of the arc of AB is 120. Measure of AF, that's at 60, so it equals 60. Measure of BC, again, since that's 120, that has to be 60. Also, there's a rule in geometry says that opposite angles are congruent. It means they're the same. This angle and this angle have to be the same because these two have to be the same. So BOC, that has to be 60, and FOC, these have to be the same, so it equals 120. I'm sorry it's taking so long, but perpendicular lines. When two lines intersect, and the angle formed angles, because when two lines cross, and you have four angles, one here, one here, one here, and here. So the angles formed are all 90 degrees. They're all right angles. Then the lines are perpendicular. The symbol we use there for perpendicular is that. So we have two lines. Let's call this one line L, and line L1 is line M. Line L is perpendicular to line M if the angles are all 45-degree angles. So let's look what happens here. You have two lines, line L, line M, they're 90 degrees. You have two intersecting segments. You have one segment and one ray. You have two intersecting rays. So if you just look at these 2 points, so they're perpendicular. You have two intersecting rays. You have two line segments like we just have here. You have one segment and one line. Here's a segment. There's a line. Yes, that's why. And then we have a ray and a segment. Yeah, a ray and a line. So when you look at what happens when two lines intersect, that's pretty much all that happens. Okay, let me see here. So let's see here. We have A, B, C. So we know that AB intersects BC. We have BA, that's a ray, intersects, perpendicular to BC, because we have also AB, the line segment, perpendicular to BC ray. So there's ways we can look at it. So are two lines perpendicular to each other. How about a line perpendicular to a plane? So remember, a plane has an infinite number of lines. So a line perpendicular to a plane is perpendicular to every line in the plane. Yeah, I'll talk about this in a second. Perpendicular planes and dihedral angles. So what are dihedral angles? Dihedral angles are when the union or the intersection of two half planes, but whenever two planes intersect, they always create, because they go on infinitely, it creates two half planes. So the union of two half planes with common lines, with a common line, because we only have one. Whenever two planes intersect, you can only have one line. So two half planes with a common line is called an AD. So perpendicular planes and dihedral angles. Perpendicular planes, when they intersect, they create 90-degree angles. Obviously, that's what makes them perpendicular. and they share one common line. So if you think about it, think of a wall. Think of a two-story building. You have a wall, and then you have that floor. It is perpendicular. It creates 90-degree angles. That's a dihedral angle. Let's look at this thing here. So you have a building. Here's a corner of a building. You have a floor. The first floor, the second floor. And then you have the floor between there. So you have the line, the two planes. You have alpha, beta. You have the two planes intersecting. Create a line. AD. So if you took 2 points, one on B, on the alpha, one on beta, S, they share a common vertex, P, then that angle created by QPS is 90 degrees. That means that these two planes created a dihedral angle, QPS. Alright, sorry it took so long, but that's the first section of chapter 11.